Hello there, and welcome once again. Here we have a question from summer 2010, and I've chosen AS3, which is the Practical Techniques assessment. And the question we're going for is a data analysis question, question 5, and it is worth 20 marks in total, so it's 50% of this exam comes from this section. Title of this question, as you can see, is maximum power transfer and load resistance. So let's read through what we're being asked. Power transferred from an electric source such as a battery to an external circuit called the load resistance depends on the internal resistance of the source and the resistance of the load. The student uses the circuit shown in figure 5.1 to investigate the relationship between the power delivered to the load and the value of the load resistance. So here's our diagram, and of course, yes, you've got our power source. You have ammeter and voltmeter in there to measure the current and the voltage, the PD, and then you also have a variable resistor, which is the load resistance. So the variable resistor represents the load resistor R. The ammeter A measures the current delivered by the source, and the voltmeter V measures the voltage across the load resistor. The student takes a set of values of V and I corresponding to different values of the load resistance R. And as you can see, it says the results are recorded in table 5.1. So let's scroll down to 5.1, and the voltages here, what they've done is they have changed up the variable resistor to allow the voltage to change on it, across it, and then the corresponding currents have been measured. So let's look now at what we're being asked. So our theory, the student plans to plot a graph of power delivered on the y-axis against the load resistance R on the x-axis. State their equation that enables the power P and the load resistance R to be calculated from the data in table 5.1. Bit of factual recall needed here. So P is equal to I times V, and R is equal to V divided by I. Next up, we're asked to process some data and calculate the value of power and load resistance needed to complete the table and record them in the appropriate number of significant figures in 5.1. Include the appropriate units in the column heading. So as well as the values, we also need to make sure we've got significant figures correct, and we've got our units. 5 marks for this. So let's go over to the table. Bam, there we go. Just number crunching time. What we've done is for power, it is V times I. Now just notice there milliamps, so this is 1.25. If we multiplying 0 by either way, it would be 0. But for the rest of them here, it's always these values divided by 1,000 to get it just into amps. So 1.14 all the way down. So that's where we get these numbers for. Resistance then is the voltage value divided by the current, and again it's in amps. But you'll notice here that what the examiners want to see is consistency with the number of significant figures. In SEA, that's what they require. So significant figures linked to the significant figures of the measured values. What we have here is our process values. They must also be to the same number of significant figures. So 3 significant figures for all these, 3 for all these. So as you can see, then we have to show these are the 3 significant figures as well. So moving on, we're now on part 2. It says, on the grid of figure 5.2, draw the graph of the process data in table 5.1. Choose suitable scales and label the axes. Plot the points and draw the best smooth curve through them. The graph should reach a maximum value for the power and then decrease as R increases. So we've been given quite a few clues here as to how the graph is going to turn out. Alright, that we have a maximum value and it decreases. It's not going to be a straight line graph, it's going to be a smooth curve. So first up we need to decide on the scales and the labels for the axes. Now I've just made a copy of this table. I'm going to bring it over to the graph just to make things a bit easier. So first of all, on the y-axis we're going to have the power. I need to choose the highest value here that we need to reach, which is 3.05, and that will decide then for our y-axis what the maximum value will be. On resistance, well, we have to include 16, so that's the maximum that it has to go up to at least. There's our axis setup. Let's just zoom in to see what we've gone for. You can see we've reached the 3.5 on the y-axis, so that will include all these values, and also on the x-axis we have gone as far as what's needed, and there's our 16. Last thing just to note as well is the label on each of the axes. There's our P for power, and then we use a slash or solidus followed by the unit W for watts, and follow on then as well down here with our R for resistance slash our ohms. Must mention as well that the axes, the scale that we've chosen has to be a convenient or a simple scale. We're looking for something that people are going to be able to read off quite easily. I mean, this is graph is really a form of like communicating your information, so it needs to be something that people can easily read. So you'll see I've chosen steps of 0.5 on the y-axis, gone up in whole units, 1 units on the x-axis. So rule of thumb is stay away from awkward scales such as 3, 7, just strange decimals. Just keep to as simple a scale as possible. Next then, let's plot the points. There now are the 6 points plotted as accurately as possible. The next thing is to draw on the curve, the smooth curved line. So there's the line of best fit now drawn as well. Let's have a quick look at the mark scheme for this, and you'll see that what we're looking for is mark for the scale. You have to use more than half of each axis. So quick look back at this and you'll see that our axes, like, I've just about gone over 50%, just about, in terms of the y's. In terms of the x, definitely stretched that far enough. Hopefully they wouldn't mark me down for that one. And what we've got then as well is the axes labelled correctly with the quantity and unit, our points within plus or minus 2 millimeters, and then a smooth curve. So I think I would get full marks for that. Okay, now let's move on to the last section, the analysis and evaluation. So from the graph, find the maximum power delivered by the source and the value of the load resistance when this occurs. Include appropriate units. So Pmax is going to be where we have our peak of the curve. So our peak of the curve is just here. Hopefully just zoom in, okay, and read across from there. Put a wee dashed line. Helps with that. It's a nice straight dash line. So what we have there is our 3.1, so 3.15. So the power is 3.15, and the resistance, well, it is like that. Well, we need to draw a dash line down from here. Go down all the way to the bottom here, nearly there. Okay, and that's going to be 8.6. So let's fill that in up here. And finally, the evaluation. How could the student have improved the experiment so that the accuracy of the values of Pmax and Rm obtained from the graph are more precise? So this is our keyword here, precise, not to be mixed up with reliable. Precise means that we get it as close to the true value as possible. And you might notice in here that this line is like the curve could be a bit slightly different. Alright, that there's a bit of ambiguity in here. So to be more precise then, rather than just having the resistances at 5 and 11, what we could do is find out, well, what are the corresponding power readings for the resistances in between. So that's how we could be more certain that this value up here is definitely at the peak. So take more readings of Rm in between 5 ohms and 11 ohms. Next, we are told it can be shown that the internal resistance of the source will equal the load resistance when maximum power is delivered from the source to the load. Under these conditions, what is the total resistance of the circuit? So we're seeing here that the internal resistance equals the load resistance. So then what is the total resistance of the circuit? Well, if we jump over to our diagram here, and I just slightly simplify this. So I've just drawn the equivalent circuit here with this being our electrical source. So the electrical source is made up of, this is our EMF and our internal resistance. So I'm just going to label this lowercase r, and the other resistance that we have in the circuit is the load resistance R. So the pair of them are one after each other, so they're in series. So we use our total is equal to R plus R. And let's jump back to the question, which asks us to what is the total resistance of the circuit, and if the internal resistance equals the load resistance at maximum power. So our maximum power, we've said up here, is when the resistance is 8.6, and if these are equal, if 8.6 is the same as the internal resistance, then of course it's just going to be 2 times the external resistance, and that then is our 17.2 ohms. Part 3, deduce the efficiency of the power source when maximum power transfer occurs. So once again, maximum power is happening whenever the external resistance is 8.6 ohms. And the equation for efficiency is the useful output divided by the total input. So we're going to use, for the useful output, we're going to put in the power of the external circuit, and the total input will be, well, the power of the whole circuit. Now, the equation we've chosen for the power is I squared Rm for the external circuit, and for the total resistance, if we've chosen I squared RT. And of course, the I squareds cancel. Rm is 8.6, RT is 17.2, and whenever we divide the two, we get 0.5. Asks for a percentage, so that then would just be 50%. To end with, we have a question. A fellow student looks at table 5.1, comments on the first reading of VNI, and asks, how can there be a current around the circuit when there is no voltage across the external load? So explain how this situation arises. So if we go over to our table, there's what he's referring to. Now this voltage is across the load resistance, but there still is an internal resistance here. So if we ignore this R over here, then there can still be a current that flows, though, even though there's no external resistance. There will be a voltage across this internal resistance.
So let's move back to the question and put our answer in here. So the internal resistance of the battery will still have a voltage across it, even though there is zero resistance in the external circuit. Okay, and as always, just to finish with, there is our mark scheme.